Hello! In this video we will introduce you to the polar form of a complex number. Recall the definition of a complex number z as x plus I times y with x and y real. Here I denotes an imaginary number with the property that I squared equals minus 1. Furthermore, x denotes the real part of z and y the imaginary part of z. Complex numbers can be displayed in the complex plane by use of their real and imaginary parts. However, there is another way to indicate the position of z in the complex plane. Consider the distance r to the origin and the indicated angle theta. Considering the unit circle, we see that x equals r times cosine theta and that y equals r times sine theta. This implies that z can also be written as r times cosine theta plus I times sine theta. This is called the polar form of the complex number z. R is called the modulus of z, and the angle theta is called an argument of z. If z is x plus I times y with x and y real, the Pythagorean theorem implies that the modulus of z equals the square root of x squared plus y squared. Because of the periodicity of the cosine and the sine, the angle theta is not unique. If we add or subtract any multiple of 2 pi, the values of the cosine and the sine will be the same. Euler introduced a special notation for the polar form of a complex number. In fact, he defined e to the power I times theta to be equal to cosine theta plus I times sine theta. In order to explain this, the right-hand side can be seen as a complex function f of the variable theta. If we define the derivative of such a complex function as the derivative of the real part plus I times the derivative of the imaginary part, then we obtain that f prime of theta equals minus sine theta plus I times cosine theta. Now we use the fact that I squared equals minus 1 to see that f prime of theta is equal to I times f of theta. This explains Euler's notation because e to the power I times theta satisfies the usual rules of calculation. Euler's formula provides us with a nice, compact way to denote the polar form of a complex number z. In class you will learn that this form helps to evaluate products and quotients of complex numbers. Using the usual rules of calculation, we see that products give rise to additions of arguments and quotients to subtractions of arguments. In class you will see how this works. See you then. Bye.